Hey guys, welcome back to another short video. Today I'm going to be taking you through the SAC preparation question related to constructing a roller coaster. So this primary activity I'll put in the first video, and then the second video I'll show you how to go about actually doing the task of building a roller coaster, and this is preparing you for the second component of the upcoming SAC. So this question, it gives us some conditions. So we're told we have an open downward parabola. So it's a parabola that is open facing downward, also called a concave down parabola, with a vertex at 9, 3. So what does that look like? So it's a parabola facing downwards like this. It's got a vertex at the coordinates 9, 3. So it's set up so it's tangent to, which means smooth and continuous with, an open upward parabola with a vertex or turning point. So vertex is the same thing as turning point. So let's just write that here. That's a turning point. It's usually what we've called it. So it's got a vertex turning point at 4, 1, passes through the point 0, 9. So basically what we're told here is it's got a turning point at 4, 1, passes through 0, 9. There it is. We need to figure out what would be the equation of these two parabolas, and specifically at what coordinates do the two parabolas meet. So we're going to need to at some point find this particular x and y value here where the two parabolas cross each other over. So how do we go about answering a question like this? Well, first up, we're going to kind of list out the information that we know. So finding the second parabola is going to be hard, but we do actually have enough information to find the blue parabola right off the bat. So the first fact that you're going to have to use here is the fact that parabola vertex form has the equation that's listed here. So I'm going to write that out in the form that you're probably more familiar with, which is y equals ax minus h squared plus k. And this is called the turning point form of a quadratic equation. It essentially has an equation written in a form where we have what's called the horizontal translation factor h and the vertical translation factor k of the turning point. So if we know the coordinates of the turning point, we know in this case it's 4, 1, then that tells us that for this blue parabola, h is going to be equal to 4 and k is going to be equal to 1. So for parabola 1, we have that y is equal to ax minus 4 squared plus k, because this parabola has the turning point plus 1. Okay, h is equal to 4, k is equal to 1. Beautiful. All right, what else do we know about this parabola? Well, we know that it passes through the point 0, 9, so therefore when x is equal to 0, y is equal to 9. So we can just sub that point in, and then we can use that to figure out what a is. So I'm going to sub in 0, 9 into this equation, and therefore we're going to find that 9, so y is equal to 9, is equal to a times 0 minus 4 squared plus 1. So I've substituted x equals 0, 9 equals y. We can expand this bracket, so we can see this is 0 minus 4, so that's negative 4, and negative 4 squared is equal to 16. Okay, and now to solve this, we can minus 1 from both sides. So we find that 8 is equal to 16a, and then we can divide both sides by 16, and we find that a is equal to 8 divided by 16, which simplifies down to a half. And therefore, we can say that the equation of our first parabola, and I'm just going to put this over here. So let's just write this over here. Parabola 1 has the equation y is equal to a half times x minus 4 squared plus 1. All right, so that's just subbing it into this equation here. Now we can actually then expand those brackets. We could do this by hand, so I'll show you how you do that. First, we'd expand this perfect square over here. We'd say, okay, x minus 4 squared is going to be equal to x squared minus 8x plus 16 plus 1. You could do that using FOIL, or you can do that using how we know how to expand perfect squares. And then we can expand this bracket here. So this is going to be a half x squared minus 8x. So we need to distribute this half between everything inside this brackets, right? So we're going to go a half times x squared, that's a half x squared. A half times negative 8x, well, that's going to be a half of 8, which is 4. And then we're going to have a half times 16, so that's going to be 8 plus 1, And 8 plus 1, well, that simplifies down just down to 9. So we can see that would be how we'd expand these brackets. And if you're not confident with that, you just really don't know how to expand brackets and you're not confident that you're going to get it right, don't worry. This is a tech active assessment, so you're allowed to use your CAS. What you can do is you can go action, transformation, and then expands. And then we could actually just type this in as is. We could just go 1 over 2 times x minus 4 squared plus 1. Boom, there we go. Yep, nice and simplified for us. That's a half x squared minus 4x plus 9. Checks out. All right, fantastic. Now, the difficulty here is now going to be figuring out what parabola 2 is. So what do we know about parabola 2? I'm going to switch to black for this. So parabola 2. Okay, so first thing we know is that it has a vertex at the point 9, 3. So we can now get an equation for parabola 1 that looks like this. Same logic as before. The turning point form of the equation, h is equal to the x coordinate of the turning point, k is equal to the y coordinate of the turning point. So that's going to tell us that the equation of parabola 2 is going to be a times x minus 9 squared plus 3. Okay, so we can expand those brackets as before. Let's just do it on the CAS just to be faster. So it's going to be, if we go a half times x minus 9 plus 3, okay, that's a half x squared minus 9x plus a fraction. So that is, so it's going to be a half. Oh, sorry, but there's the a there. Yeah, we'll just do it by hand. That's right. So it's going to be what's that doing? There we go. A times x squared minus, okay, 2 times 9 is 18. X plus 81 plus 3. Okay, and then we expand this bracket. So I'm going to distribute the a between everything inside the brackets here. So that's going to be a times x squared minus 18ax plus 81 times a. So I'm multiplying a by everything in the brackets, plus 3. Beautiful. Okay, so there's our equation for parabola 2. All right, so let's write that over here. Parabola 2 has the equation y equals ax squared minus 18ax plus 81a plus 3. And at this stage, we do not have enough information to find out what a is, unfortunately. So how are we going to do that? How are we going to figure out what a is? Well, what we do know about this particular function here is that, well, we're trying to design this equation such that it's going to pass through this particular point. By the way, if we were to currently just plug in what this looks like, what we have so far into our Desmos graphing calculator, let's just try and understand what we're doing here. So if I typed in this equation, minus 18 ax plus 81a plus 3. And if you add a slider for a, you can see that what's happening here is we've just come up with the equation for a parabola that has its vertex at the points 9, 3. And if I vary the value of a, the vertex is always at that point, but it's just changing like the shape of the parabola. So that a factor is like the dilation factor of our parabola here. It's the dilation factor with respect to the y coordinate, because as we can see, yeah, it's affecting the parabola like that. We need to see what particular value of a makes this so that it lines up with our other parabola. We could actually do this using sliders. So if we typed in our second equation, y equals a half x squared minus 4x plus 9, we want to figure out where these two parabolas can be tangent with one another. And by pure coincidence, that's actually looking pretty good right there. But if I vary the value of a, it's hard to find the exact point, and we might need to play around with it a bit. It might be like 2, where is it? 0.01. Yeah, it's hard to find. 0.9, it's a bit more than that. And then we've overshot it, so it's pretty hard to find. It might be around, but yeah, it's really hard to find as an exact value. So how do we go about doing that? Well, what we're going to do is we need to ask ourselves, what do you know about this point here? Well, this purple point, x1, y1, we know that at that point, the two parabolas have the same y value. So let me write this in purple. So at x1, y1, y1, well, if I plug y, like a particular value of x, whatever this x1 value is, into this equation, I'm going to get out the same value that I would if I plugged it into this equation, right? Because this point here lies on both the blue parabola and on the black parabola. So what we have is that that equation there must be equal to this equation here. The two y values are the same. So to set that up as an equation, we have that this particular x value, if I plug it into the first equation, it's going to be the same. It's going to give me the same y value, let's call it y1, that I get if I plug it into this equation here. 18a x1 plus 81a plus 3, right? That's the first piece of information I have. The second piece of information I have is that the derivatives of these two parabolas need to be the same at this point in order for this to give me a smooth and continuous function. Now, just keep in mind here that what I've actually set up here, this first equation, is not enough for me to figure out what a and x are, because as a general rule, if I have two unknowns, in this case, I don't know what a is and I don't know what x1 is, I need two equations to figure out the two values of those unknowns. So I want to figure out what x1 and a are. I need a second equation. Where does that come from? It comes from the derivative, because at that point, that purple point, the derivative of the blue graph, in other words, its gradient, must be the same as the gradient of the black graph. So how does that translate? Well, what that means is the derivative of this function needs to be equal to the derivative of this function here. So I'm just going to do that as an aside over here. So for P1, so let's say consider derivatives. So let's start with P1. So for P1, the derivative is equal to, well, it's just going to be the derivative of this. So to derive this, I'm going to go 2 times a half, then I count down x by 1, so 2 times a half is just equal to 1. So this is going to be x minus 4, because the derivative of negative 4x is 4. And then for parabola 2, we're going to get a similar sort of result. So parabola 2, we have that dy dx is going to be equal to, okay, so we look at this black equation over here for P2, that's going to be equal to 2ax minus 4. And you can do this on the CAS if you need to. Now, again, like I said, the two parabolas must be equal, so the two derivatives must be equal at this particular point, x1, y1. So that gives us that equation for the first derivative must be equal to the equation for the second derivative. So we can set this up as a system of equations. Again, we have that x1 minus 4 must be equal to 2 times a times x1 minus 4. And this gives us a system of equations that we can now solve. So therefore, what we're trying to solve on CAS is the following. We want to solve when is this first equation, which is this first one here, where the two functions are equal. We want to solve that equation to figure out what a and x is, and we want also a value of x and a that satisfies our second equation. So this one here, where the two derivatives are equal. We're solving this for a and x, so that is exactly what we would type into the CAS calculator. So I'm going to go solve. No, sorry, not solve. We're going to click this button here. So for simultaneous equations, we just type it in. We go 1 over 2 times x squared minus 4 times x plus 9 is equal to a times x squared minus 18 times a times x plus 81 times a plus 3. Second equation, x minus 4 needs to be equal to 2 times a times x minus 4, and we're solving for a and x. And it tells us that the values there, that doesn't look quite right. All right, I think I've made a mistake somewhere along the line, so let's bear with me while I figure out where I did that. Sometimes it doesn't like it if I don't include those symbols. No, so it was a half. Yep, that's good. And then we have a times x squared minus 18ax plus 18 times 81 times a. First equation looks good. And then the second equation, I think we've forgotten a here somewhere. Yeah. Okay, so that second equation was wrong, unfortunately. So the derivative of that black function, I'm sure you guys following along at home picked up on this. So I made a mistake finding the derivative of this function here. Let's just look at the wrong line. So the derivative of that function should be 18a, right? So that's going to affect this one here. That should be 18a. This should be 18a. Okay, so that's just, I took the derivative of this equation here wrong. The derivative is 2 times ax minus 18a. So plugging that into what we had up here, let's change that to 18a there, and there's our good solution. Looking good. Okay, so we've got that. Let me just fix this up a little bit and write it down so we can recall what we have. So therefore, we have that a... Ooh, I hate it when it does that. So we have that a is equal to negative 2 over 21, and x1, which is to say the x-coordinate of this point where the two parabolas are tangent to one another, is equal to 24 over 5. Okay. So we would need to do a couple of things here. We need to figure out what the y-coordinate of this point where the two lines cross over is. So we found the x-coordinate. How do we find the y-coordinate? Well, to find the y-coordinate, we just plug this number into either one of the two equations. We could plug it into that purple one. And also to find what the equation of the second line is, we're going to substitute a equals negative 2 over 21 into this black line here. So let me just do that for you. So therefore, we can find that the equation for parabola 2, well, we had this equation here before. Y is equal to a times x squared, etc. We just found to this line here. So we just found that a is equal to negative 2 over 21. So I'm just going to substitute that into the equation. So negative 2 over 21 x squared minus 18 times negative 2 over 21 x plus 81 times negative 2 over 21 plus 3. You can simplify that down and you'll see what the equation is equal to. And then to figure out the value of y is, we just need to plug it into each of those two equations. Now, just to wrap this up, as we can see here, if I set that up as my equation, so in fact, we can just simplify this down on the CAS. I think if we just type that in as an expression straight up, it should just simplify it for us. So we can say negative 2 over 21 times x squared minus 18 times negative 2 over 21 times x plus 81 times negative 2 over 21 plus 3. There we go. There is our equation. And if we plug that into the Desmos program as our second equation, we're going to see that this is equal to, should be a line that passes through these 2 points. Let's see if it works out. So minus 33 over 7. Yep, there we go. So as we can see, the two parabolas are now tangent to one another, smooth and continuous at that coordinate there. And the way you'd find this number is plugging in your x-coordinate that we found was 4.8, which is the same thing as 24 over 5. All right, so that's how you would go about answering this question. That's a very useful procedure for you to be aware of. And you'll be using this methodology that I've just shown you here in your part, the SAC, which I'm going to get you started on in the next video. So next video is going to be how to design a roller coaster using calculus. So watch out for that one. I'll try and release it as soon as possible. Just keep in mind that you won't need that one for next week's component of the SAC. It's going to be the week after, so don't worry too much about that just yet. Focus on the previous two videos for now. But yeah. All right. Thank you very much for watching, guys. I will see you guys next week. Good luck for the first part of the SAC, and I'll see you in class. Have a good one.